discussing a paper that was recently published out of Stanford, S1. It's test time scaling and low budget training for reasoning. So what this people are trying to attempt is to reproduce O1, which is a reasoning model out of OpenAI, R1, a reasoning model out of DeepSeek, and other reasoning models such as Grok, Think. The idea behind reasoning models is to take the pre-training model, which has been pre-trained on trillions of tokens, and activate a problem-solving function that is allegedly already inherent in the model but needs to be activated. So this is a little bit similar or actually the same like the alignment problem with models. So think about it this way, like you have a pre-trained model and now you want to extract knowledge from this model, and you want this model to do certain things. So when it extracts that knowledge, you want it to do it in a certain way. So what that means in plain English is that first and foremost, you want the model to be able to solve the problem. And then in the alignment community, of course, there's also this concern about the model doing the right thing and not saying the wrong words and things like that. This particular paper is not so much about the sort of this ethics alignment, and it's more about actual problem solving. And what they introduce is a new test time scaling method that they call budget forcing. The paper's attached in the show notes, so please read what these things actually mean. But what I want to discuss here is a more general concept, which is the idea of test time scaling, and a couple of interesting thoughts that I gathered from the paper. So what is test time scaling? It means that when you test the model, so you pre-train the model, and now you're applying problems to it, you're prompting it with problems, and you're testing the model, so you're testing the traces, so the sort of logical chain of thought processes that lead the model to find solutions, and you're testing them, so you're trying to find better ways to solve the problem. And there's a sequential way to do that and a parallel way to do that. Let's focus on the parallel way, which is maybe a little bit more intuitive. So you're exposed with a problem, let's say a certain math Olympiad problem, and now the model can in parallel try many solutions to the problem. It can try different chains of thought. And what the authors are doing here is finding methodologies to either increase the compute at test time, so in other words, try more, or force it to stop trying. And what the author says in an interview that he gave on the Twimmel podcast, shout out to Sam Charrington, as usual, very inspiring what he does over there. So what the author does, says on the podcast is, he says that that it's important to have the model generate traces, and for training, it actually doesn't even matter if the traces are correct or not. The traces, again, it's a sequence of chain of thought that lead to the solution of the problem. And what the authors are finding is that even when bad traces are employed, those traces can be used for the pre-training phase. And that's, by the way, something echoed by Jensen Huang in the recent earnings call, which he was asked about R1 and things like that. And he said that these reasoning models actually generate new data. I wouldn't even call it synthetic data. This is real data. This is models trying to solve problems. And when they can't find solutions to problems, that in itself is useful information for pre-training, because as much as it's useful to understand how you get to a solution, it's also very useful to understand how not to get to a solution, particularly when you use reinforcement learning, because reinforcement learning is the process of figuring out a way to find the solution. And I'm paraphrasing the author here. He says, supervised fine-tuning, which is the classical method of telling the model what's right and what's wrong. This is akin to teaching a fisherman how to fish, versus reinforcement learning is teaching a fisherman what the taste of fish is so he can figure out its solution by itself. So really important insight here that when you apply reinforcement learning to fine-tuning models for reasoning, actually wrong paths are as useful as right paths, because the model can learn from those wrong paths and divert itself to the right path. If you just give it the right path, then it might not be able to switch when it's on the wrong path to the right path. So it needs to have enough wrong path information to remember, oh, I see, this is one of those wrong paths. Let me not do this. Let me do something else. So that's the way I interpret this. So this is really important. Again, reasoning models create data about problem-solving solutions or problem-solving templates that are useful for, particularly for reinforcement learning, when the models are trying to find the solutions to certain problems. What are we talking about here? We're talking about classical sort of brainy problems such as math Olympiad problems, quant questions in interviews, things like that. So really difficult logical questions. And what the models are doing is learning how to reason. So learning how to generate chain of, I call this sort of chain of thought generation, or applying templates of chain of thought to certain problems. So think of it like the model recognizes, oh, this is one of those problems where you need to do quadratic programming to find an optimum. Okay, let me use the template for quadratic programming and see how far I get. And what the authors are doing here, again, test time scaling, just means that for certain problems, you want to use more compute at test time, and for others less. You don't want to use the same for all. That way, you kind of optimize the training method and the time and the budget for training, and therefore you can probably get much faster, much better performance. Another very interesting insight from the paper is the data curation. So the way they fine-tune the model is they start with 59,000 problems and distill that down to 1,000 problems. They use 1,000 problems to fine-tune the model. And what they emphasize in the paper more than once is the importance of the curation of those problems. They have to be diverse. They have to have a certain, intellectual, if you will, or logical trace that makes sense. So they can't just be a random solutions, sort of the genius light bulb type stuff. It should be more structured, so the model can actually learn a certain structure to solve problems. And what's really important here is also that when you do test time scaling, you can very quickly test whether the model has the right or wrong solution. So these are not problems like with open-ended answers. This is not a problem like, for example, what's the best way to solve climate change, or how do we increase equality in society? Those are not problems that can be solved very easily, where the solution can be checked versus right and wrong. So this goes back to the same old problem in AI, which is eval, right? If you have a clear eval, you can iterate much faster and get much faster, better results. That's why math, coding, logical problems are really fast and will improve even faster in the near future. And we'll have really good reasoning models for math, physics problems, and the kind of stuff versus the more fluffy stuff, as I like to call it, not with the degrading bitone. In fact, this is almost a Moravec paradox, right? That the hard stuff is easy to program, so the really hard logical STEM type stuff, and the easy part seems to be really hard. Meaning the easy, we think, things like biology, history, philosophy are easier because they're not as rigorous, but then they're much harder to program because the eval is hard. The eval is hard. So to summarize this paper, I think it's also the interview. I mean, both in conjunction are good introductions to the problem of reasoning models and fine-tuning, test time scaling. I think it explains some of the trara that has been going on recently around DeepSeek and O1 and now S1. This paper is called S1. The reasoning again is really finding templates for solutions, and test time scaling is finding a method to apply more compute to certain problems when necessary and cut off the compute when the problems are either solved or maybe also when the trace is not going anywhere, cut it off, start again. So finding better, more efficient ways to apply the compute to test time, because you can drastically improve the performance by having maybe a few more steps in the trace, and you can also lower the budget by cutting off when it's not going anywhere. Thank you.